So continuing on this discussion of vapor pressure, I wanted to show you this graph and explain to you what this Clausius-Clapeyron equation is. So this graph is showing you temperature on your x-axis and then vapor pressure on your y. And this is in torrs. Just understand 760, this line across is atmospheric pressure at sea level. So I have 4 different substances. I'm just going to focus on the first 3, the ether, ethanol and alcohol, and then water. What I want you to focus on is where these curves essentially intersect with that line, okay? So each one of these curves is, depending upon the temperature, what is the vapor pressure you will produce above that liquid, okay? So again, the higher the temperature, the more your vapor pressure is going to increase because you're going to give more and more energy to those particles to become a vapor. So essentially the normal boiling point of ether is 34.6, ethanol is 78.3, and of course we know water to be 100. So if I take a look at each one of these, and again for the ether and the alcohol, I will draw it for you and show you what you want to focus on. So ether, alcohol, and water, what this graph is telling you is ether has a very high vapor pressure as you keep increasing temperature. So it has what we call weak forces. The only thing this has is probably dispersion forces in the molecule, okay? While alcohol and water, because of this OH, okay, is going to have hydrogen bonding. So both of them have hydrogen bonding. But if I gave you data like this, what can you say about the ethanol, the alcohol versus the water? Well, the alcohol is going to have less, it's going to have more vapor than the water does. Even though they both have hydrogen bonding, water is a definite outlier. It is so unusual. It is a small molecule. Ethyl alcohol is 2 carbons. I mean, it's, you know, a relatively larger molecule. You would think that water would have a lower boiling point than an alcohol would, but it doesn't. So what would the picture look like? So ether, you would have a lot of vapor in there, okay? Alcohol, you would have a lot, and then water, very little in comparison, let's say. Now think of, again, this picture as meaning this has high vapor pressure versus water, which has low vapor pressure. Okay. So again, the other way you can look at this graph is to say at 20 degrees Celsius, okay? Water is going to be a small amount above the liquid. Ethanol is going to be there, but then ether is going to be way up here. So again, when you're looking at this graph, that's what it's trying to show you, is that relationship. Okay, so again, more temperature, more vapor pressure, but every substance is going to have a different vapor pressure depending upon the forces. The stronger the force, less likely it is to go to vapor. Now, this graph is then a graph below it. Well, the reason we have this is something called the Clausius-Clapeyron equation. It used to be a big focus, no longer. If we have a curve, we don't like curves. We want to make them align. Okay, and the reason we want to make things align is because it's easy to predict off of. So we have y is equal to mx plus b as our form of a line. So what we could do is we could take this curve data and make it into a straight line by taking the natural log of it. So this is called the Clausius-Clapeyron equation. Okay, different pressures is going to affect, with the different temperatures, what is the heat of vaporization. So used to be an emphasis on this. Again, I just kind of introduced it to you for you to kind of understand. This particular graph on top can really be derived or converted into a straight line so we can predict data off of that. But there is less emphasis on this than there used to be, so that's why I kind of put it off to the side. But I still like to talk about this particular graph because it's so very important for you to understand that in terms of phase changes. So speaking of phase changes, we are going to kind of, at the end of this lecture, get a little bit more into maybe the thermo in terms of energies. How much energy are we talking about? So when we're talking about going from a liquid to a vapor, if we're going from a solid to a liquid, and even going from a solid to a gas, heat is absorbed, okay? And what you get is something with more and more entropy or freedom. So entropy is a capital S. And again, we're going to talk about entropy here and there. And we'll focus a lot on it at the end of second semester. But what this is trying to show you is gases have the most freedom, okay, while solids have the least. Okay, and if we think of their structures, again, we spent chapter 10 talking about gases, and these two chapters are focused on liquids and solids. Solids, think of that cubic structure. Again, not too much focus on that, but realize that that's locked into place. So those atoms can't move, those ions can't move. While gases, they can bounce around in a container and change, interact. So therefore, energy is released as you go from a gas to a liquid or a liquid to a solid. So what we're going to be discussing are two things. Heat of fusion, okay, heat of fusion, which is the enthalpy of fusion, is the energy needed to melt 1 mole of a solid substance at 1 atmosphere pressure. Again, you need standard conditions for this to be valid. And then you have enthalpy of vaporization, which is delta H of VAP. Okay, again, so solid going to liquid, liquid going to gas, okay? And these units are going to be what we've seen before. So they're going to be in kilojoules per mole is going to be our standard. So this graph is on page 458, and I'll put that in your notes as well. I like to show this because it gives you some perspective on heat of fusion versus heat of vaporization. And even heat of sublimation, okay? So if you take a look at this graph, we have butane, ether, water, and mercury. And in the pinkish color, you have heat of fusion, you have heat of vaporization blue, and then green is heat of sublimation. So if we just look at the diethyl ether, what are some patterns or things that you could tell me about this graph? Well, you could say that 7 plus 29 gives me 36. So obviously the heat of fusion plus the heat of vaporization gives us heat of sublimation. That's why we don't focus too much on heat of sublimation, because again, it's just the adding of the two. But do notice heat of fusion for all of these substances is lower than heat of vaporization. Okay, so heat of fusion is going from solid to liquid versus heat of vaporization is going from liquid to gas, liquid to vapor. Okay, so why do you think there's a big difference between heat of fusion and heat of vaporization? Well, think of forces, okay? It's probably not as much energy to go from a solid to a liquid than it goes from a liquid to a vapor. Okay, that's a huge jump there, because you got to remove most of those forces in order for it to go to vapor. So that's why I like this graph, because it kind of shows you that in a very easy format for your brain to kind of absorb. So as I said, that page number is 458, so you can kind of write that down in your notes. So what I'm going to finish up with here is this is what I call the heating curve in terms of heat of vaporization, heat of fusion. So I drew this heating curve of water. We always do water because we understand water in terms of its states of matter at different temperatures and situations. So we have heat on the x-axis and we have temperature on the y. So please realize that 0 degrees Celsius is where water freezes or it melts. And then at 100 degrees Celsius we have boiling or we have condensing. So these plateaus, okay, where the line is going straight across, okay, this is where we have no change in temperature. That's what it's trying to show you. So this is where water is a solid, this is where it's a liquid, this is where it is a gas, okay? And so at each one of these plateaus, we have a different delta H, okay? So this is delta H of fusion because I'm going from a solid to a liquid. Up here, this is delta H of vaporization. So I call it delta H of MAP, my favorite one. Realize I'm going from left to right. If I'm going from left to right, I'm adding heat as I go from left to right. If I go from right to left, I am then subtracting heat. So I could change these underneath to negative delta H's, and they have different names, okay? This is heat of condensation, and this is heat of solidification. Again, you don't usually talk too much about those because they are the same numerical value. The only difference you have is going to be direction, okay? So if I am talking about how much energy does it take to go from a solid to liquid, please realize that this is where delta T is 0, okay? There's no change in temperature at that point. These upward sloping lines where it's all solid, all liquid, all gas, you can use, of course, Q is equal to MC delta T to find how much heat is required there. So again, this is going to feel a little bit like thermo because of the fact that we're going back and talking about how much energy things are taking, okay? So that's why it's going to feel a little bit similar to that. So because I have different states of matter, I'm going to have different specific heats. So specific heat of water, of course, is 4.184 joules per gram degrees Celsius. But if I have the specific heat of ice, that's going to be different versus the specific heat of vapor, okay? So with this, we're going to do a series of calculations to kind of understand this graph.